Acid chlorides. So an acid chloride is a derivative of a carboxylic acid in which the hydroxyl portion has been replaced with a chlorine atom. So the general formula is like this. With the carboxylic acid, come on, iPad, drawing mode please. I don't know why I had to think so long about that. The carboxylic acid looks like this. So this is a derivative. It's like a carboxylic acid, but it's changed a little bit. So you take off the OH and you put on a chlorine, and that's called an acid chloride. There are two methods for naming these. One is to replace the ic acid ending of the common name with il chloride. And so this acid chloride is a derivative of butyric acid. So butyric acid, frogs are polite being, right? 4. That's wrong. That's got 5 carbons. Okay, we can fix that. That's not from butyric acid, is it? Come on. How's that? That's better. Butyric acid has 4 carbons. That was pentanoic acid. Butyric acid would become butyryl chloride. So you take the name of the acid and take off the ic acid part and you put il chloride. So butyric acid is the common name. What's the IUPAC name for that acid? Butanoic acid? Right? So if we're using that name, the going to the il chloride it gets a little ugly. So that's where the second method comes in. Take off the oic acid ending and replace with oil chloride. So if we're using the IUPAC name, butanoic acid would become butanoyl chloride. And the other example here, if this had an OH here, it would be 3-methylpentanoic acid. Let's check that. 1, 2, 3. 3-methyl, 4, 5. Okay, so they got that one right. 3-methylpentanoic acid. So you take off the ic acid, well, take off the oic acid and replace it with oil. So 3-methylpentanoyl chloride. Any questions? Acid chlorides are made by reacting that parent carboxylic acid with an inorganic chloride. There's several different ones that will work. But we take the acid here, we react it with a chloride, and it substitutes the chloride in for the hydroxide. Acid chlorides are very useful as starting materials for synthesis of other carboxylic acid derivatives, like esters and amides, because they are very reactive. They react rapidly in water to regenerate the parent carboxylic acid. So if you take this acid chloride and add water to it, the OH will come back and you'll get your original carboxylic acid back. So these acid chlorides are not present in living tissue because everything in the body is pretty much aqueous. And so anytime they come into contact with water, they turn right back into a carboxylic acid. Another group of carboxylic acid derivatives are the acid anhydrides. And so here we have this carboxylic acid, and the OH group is replaced with basically another carboxylic acid. So we formed esters between carboxylic acids and alcohols. Here we've got the OH group of an acid forming like an ester here. And these are called acid anhydrides. And you can think of them in two different ways. You can think of it as two carbonyl groups bonded with an oxygen in the middle, or you can think of it as two acyl groups bonded together. So you can take two carboxylic acids and join them together, and that makes an acid anhydride. Actually, let's draw something here that I think helps us to understand a little better why it's called an anhydride. I think my iPad's tired. It's really acting out on me right now. Come on. I want the previous slide. Thank you. Now can we do drawing mode on the previous slide, or is that too much to ask for? Okay? No? Like the YouTube people are really going to appreciate this. She's talking to her iPad. That's okay. I don't care what they think. So here's two carboxylic acids. When these join to form an acid anhydride, we pull out a water molecule. Anhydride reminds us of anhydrous. Anhydrous means without water. So you've taken two carboxylic acids, removed a water molecule, and then you end up with this acid anhydride. That's how I think of making them. That's not actually how we make them, but there are symmetrical ones where you just have two of the same carboxylic acid joining together. So when we look at them, the R groups are the same. So in this example here, this has a methyl group and that has a methyl group. With the symmetrical ones, what we can do is we can just take the name of the acid that it started with and swap anhydride for acid. So let's look at this guy. Come on. I just want to draw on you. Is that too much to ask for? Apparently it is. Okay. So this comes from what carboxylic acid? How many carbons? 2, right? You want to do the common name or the IUPAC name first? What? IUPAC 1. Okay, so IUPAC name with 2 carbons is based on ethane, right? So that would be ethanoic acid. So this anhydride was made by combining 2 molecules of ethanoic acid. And so its name is ethanoic anhydride. Let's get all the letters in there. Good grief. Common name. Frogs are polite, being very curious. Okay, so frogs are, that's acetate or acetic. So this is acetic acid, so it would be acetic anhydride. Any questions?
So for the common and the IUPAC, we keep the same last part for both would be anhydrides?
Yes. Yes, regardless of whether you're using the IUPAC or the common type of name, we swap acid for anhydride. Because if this was ethanoic acid, there would be an O and just an H here. So we've removed that H and stuck on another ethanoic acid molecule. Or we can call it acetic anhydride, using the common name for the acid. We can also have mixed acid anhydrides where it's not symmetrical. One R group is different from the other. And then we just take the names of each of those parent carboxylic acids and we list them alphabetically, and then we put the word anhydride at the end. So let's look at this guy. Over here, we've got, that came from a carboxylic acid with 3. Let's just do common names, because actually the common names are more common. We'll just do the common one for this. So, father ate, no, sorry, I'm mixing my mnemonics. Frogs are polite. So that's propionic acid. And this one over here is 2, which is acetic acid. A comes before P. So this is acetic propionic anhydride. Okay? How do you make these? You can't actually just take the 2 carboxylic acids and react them together. That doesn't work. The acid anhydrides are actually prepared by reacting an acid chloride with a carboxylate ion. So a carboxylate ion is a carboxylic acid that has lost a proton. So if you put this in a more basic solution, the proton will come off and you get the ion. If we react this with the acid chloride, then we form this acid anhydride. So that's how they're actually made. If you expose this acid anhydride to water, it will hydrolyze back to the original carboxylic acids. But you can't just get the 2 carboxylic acids to join up and become the acid anhydride. So we need to mention acyl transfer reactions. Compounds that have acyl groups can react with alcohols or phenols to form esters. And just to remind ourselves what an acyl group is, it's that portion of a carboxylic acid that remains after you take off the hydroxyl group. So carboxylic acids contain acyl groups, acid chlorides, and acid anhydrides. They all contain an acyl group. So this acyl group can react with an alcohol to form an ester. The acid chloride can react with an alcohol to form an ester. The acid anhydride can also react to form an ester. So you could get the same ester from different starting materials, but these starting materials are very similar. They've got that acyl group there. So an acyl transfer reaction is a reaction in which an acyl group is transferred from one molecule to another. And the reason we're touching on some of these things that we're not going into much detail about is we're going to see them later when we look at some of the protein synthesis and metabolic reactions in the biological chemistry. So this acyl transfer reaction is something that happens very frequently in your body. It's going on right now. Acyl groups are named by, the name is based on the acid name, and we just get rid of ic acid and use the suffix YL. So this came from acetic acid, so this is the acetyl group. So that could be attached to something else. An acyl transfer reaction could attach this to something else. The IUPAC name, this is ethanoic acid, and so this is ethanoyl, an ethanoyl group. I'm looking at this and thinking, you know, back when they were telling us how to name the chlorides, they were not consistent. I'm going to let it go. Just going to let it go. So this is from propanoic acid with 3 carbons. So propanoyl group, or propionyl group from propionic acid. If you look at the ingredients lists on your hair care products, shampoo and conditioners and stuff, you'll see a lot of these suffixes. I know one of the things that's in there is sodium lauryl sulfate. Okay, and the lauryl is an acyl group. Inorganic acids like sulfuric acid, phosphoric acid, and nitric acid can also react with alcohols to form esters. So we've looked at how carboxylic acids react with alcohols. Inorganic acids can do that as well. So here's sulfuric acid. And so this OH group here and the hydrogen from the alcohol are going to go off as water, and the main part of the alcohol is going to be attached to the sulfuric acid. So this is a methyl ester of sulfuric acid. This can happen with phosphoric acid and with nitric acid as well. So we can get esters with inorganic acids and alcohols. The phosphate esters are the most important from a biological standpoint, and again, we're talking about this now because we'll see it later. So a phosphate ester is an organic compound, and it's formed by reaction of an alcohol with phosphoric acid. Phosphoric acid is a triprotic acid, and so we could have a monoester, where we just have one ester, or we can have a diester or a triester, because each of these hydrogen or hydroxyl groups can react to form an ester. The phosphoric acid itself can spit out, that's how I think of it anyway, spit out some water and form a diphosphoric acid. So it's a little bit like an ester, and yet it isn't. And then there's something missing in there, isn't there? They're showing a diphosphoric acid reacting with another phosphoric acid to form a triphosphoric acid. What's missing? You see it? I didn't see it when I was making the slides. Right? Those just can't disappear and reappear. I need to have a talk with the publisher, I think. Anyway, this is a triphosphoric acid. All 3 of those, the regular phosphoric acid, the diphosphoric acid, the triphosphoric acid, can react with alcohols to form esters. When the diphosphoric acid reacts, then we have a diphosphate ester, or we can have a triphosphate ester. And when these form an ester with adenosine, we can have adenosine diphosphate or adenosine triphosphate. And these are abbreviated ADP and ATP, and these are very important parts of metabolism, and we'll revisit them later. A phosphorylation reaction. Well, phosphoric acids and the anhydrides are going to exist as ions in solutions that are neutral or slightly basic, which includes most bodily fluids. So in your body, this phosphoester is going to be in an ionic form, not in the neutral form. And so that's why you're going to see these written this way. So On the end of this is a phosphoryl group. That phosphoryl group can get transferred to another molecule, and we call that a phosphorylation reaction. You're transferring a phosphoryl group from one to another. An acylation reaction, ACYL, is transferring an acyl group from one to another. So we can get a triphosphate transferring a phosphoryl group to something else, and then what we have left is a diphosphate. And this is the process that occurs when ATP becomes ADP. And there's energy involved, and this is one way that your body does what it does. It's really cool. End.